Now, as promised, we're going to look at one of these discrete linear dynamical systems where the matrix that defines it has a special form. So the same value down the diagonal, almost the same values along the anti-diagonal. They differ by a sign. This is negative, this is positive. Matrices of this form have eigenvalues of A plus or minus BI. So the real and the imaginary part of the eigenvalues appear right here in the matrix. Very convenient. And let's define the length of this eigenvalue. If you've worked with complex numbers in any detail before, this formula should be familiar. If you haven't, it's easy enough to see. Here's the complex plane. Here's the real axis. Here's the imaginary axis. A plus BI has a real part of A, an imaginary part of B. This is its length. And this then is just a statement of the Pythagorean theorem. Now, even if you already knew that, this diagram is worthwhile. We're going to use it to define an angle theta. And now we're going to take this matrix and we're going to do two things to it. And we won't worry about why until a little later. But the first thing we are going to do with this matrix is factor out a scalar r. And that gives us these divisions. And then we look back at this diagram and we say that A divided by R, for example, is an adjacent side over a hypotenuse, so it's a cosine. And all of these fractions can be rewritten in terms of the sine and the cosine. What good is any of this doing? Well, you've seen this matrix matrix before. There's no real reason you would remember it. We spent maybe 5 to 10 minutes on it, like a month or so ago, and then never looked at it again. But what this is a rotation matrix. And we discussed these when we were first looking at linear transformations. We observed that taking a vector and rotating it by a fixed angle is a linear transformation from R2 to R2. And any linear transformation is equivalent to matrix multiplication. And in particular, it's equivalent to multiplication by this matrix. So if you take a vector and multiply it by this matrix, that's equivalent to rotating the vector by theta. But this means we know what multiplication by this matrix does. So suppose we have a vector that we want to multiply by this matrix. So we're in R2 and our vector x is here, let's say. Well, we know we can rewrite this matrix. We did so up here. This product is the same as R times the cosine of theta, the negative sine of theta, the sine of theta times the cosine of theta times x. And this multiplication is associative. So let's put some parentheses in there. And let's now ask the question what this multiplication is doing. Well, we do this multiplication first because it's in parentheses. And that is a rotation. Then we multiply by R, and that scales the length of our vector. So multiplying repeatedly by this matrix keeps rotating it by theta and scaling its length by a factor of R. So you see, we get rotational activity exactly like I predicted earlier when I said that complex eigenvalues give rise to rotations in the plane. So you can clearly see my limits as an artist laid bare for all to see here, but there's a computer generated example in the notes for you to look at.